Our topic today is continuing what we were doing on Wednesday, looking at measurement and uncertainty. And we're going to now kind of move away from that in a sense to talk about accuracy and precision. So we talked about uncertainty, and uncertainty certainly has a role in determining how we view measurements. You saw in lab over the past 2 days, different glassware, different equipment has different amounts of uncertainty to it. And usually, uncertainty and accuracy can be kind of viewed hand in hand. The more precise something is, the more accurate it tends to be. We saw that in the glassware. Graduated cylinders tend to do much better job at being accurate than beakers and flasks did. And even if you got, let's say you needed 17 milliliters for your Erlenmeyer flask, and let's say that you did the work and you did the calculations and it came out to be 17 right on the nose. Chances are what you saw there was that you got lucky. And if you had looked at other people's data and gone around the room and talked to other people, you would have found wide variability in that measurement with regard to the 17. Some come out at 19, some come out at 14. There's a lot of variability there. So in a single data point, it's not terribly difficult to get it right once. The true measure of precision is not just getting it right once, but is that something that is repeatable? And so precision we talk about in two kind of ways. One way we can talk about it is in terms of reproducibility. I have something that is reproducible, and so I measure that cup on the balance, and it doesn't matter how many times I measure that cup on the balance, it seems to always fall within a very tight window range of measurements. That's precision. We can measure precision by range. So if we see something like this, where we have a range of values, we can express that uncertainty, that level of precision, as plus or minus whatever the uncertain range is. So on a balance, it would probably be expressed as plus or minus 0.01. Because our balance reads out 2 decimal places. That last decimal place has a little bit of variability to it. And you saw that in the lab yesterday as well. Even if I'm weighing the same cup over and over and over and over again, it is possible that it wiggles a little bit on that last value. And that's just the uncertainty of the balance. There's nothing that we can do about it. That's just how it is. It doesn't matter what balance we would use, we get the same kind of results each time. Accuracy, on the other hand, we talk about closeness. How good is our measured value? So even if we have precision, precise measurements that aren't accurate still aren't very useful to us. So accuracy talks about how close is a value to the measured true value of a substance. So what you did yesterday as a test of that was in activity 3, where you measured the substance and you took a look at it from the perspective of, okay, here's what the real density of water should be. Here's the mass. This is how much volume is actually in there. This is how much volume I said was in there. How close are those two values to each other? Now, when it comes to calibration for certain types of instruments, there's a number of ways that we can go about it. So for balances, we usually calibrate them by weighing out an object of a known mass. So if I want to calibrate one of the balances upstairs, manufacturer sends us a piece of metal that is, I think, 25.00 grams. We put it on the scale and we check. Okay, it says it's 25.00 grams, balance is working okay. Uh-oh, it says that it's 19.47 grams. We need to recalibrate. Something's not right with the electronics. Maybe something's wrong with the balance itself and we need to replace it. Thermometer accuracy, usually done by measuring temperature for phase changes. For most, it's done with ice water. If you have a thermometer in your home, in particular like a cooking thermometer, a meat thermometer, one of the ways that you can calibrate it is you put it in, you dunk it in ice water and you let it go all the way down and you check. Okay, is it reading 32 degrees Fahrenheit? If it's not, there's usually a knob or something that you can adjust on it, if it's a digital thermometer, to help you to recalibrate it to read the right temperature. All right, so let's look at a problem like this. I've got 3 nails here. The first one weighs 13.47 grams. The second weighs 13.43 grams. The third one was measured on a different balance, and it weighs 13.4653 grams. Relatively simple question here. What is the total mass of these 3 nails? Now, to answer that, we're going to need a calculator of some kind. And so if I put in those values, 13.47 plus 13.43 plus 13.4653. If I add all those together, my calculator says 40.3653 grams. I'm sure your calculators would all say the same thing, or all do say the same thing. The question is this: is that answer good enough? Is that what we would think of as the correct answer for this problem? If you can catch the hint of foreshadowing in my voice, the answer obviously here is no. Something's wrong here. And the thing that is wrong is that we haven't accounted for the uncertainty. Remember, every single measurement carries with it some level of variance, some amount of uncertainty. Our job as scientists is to minimize the uncertainty as much as possible. And so to do that, we have to make sure that we have as little uncertainty in our calculated values as possible. This is where significant figures come in. So if I look at it from a standpoint of uncertainty, the uncertain digit in that first nail is the 7 here. The uncertain digit in the second nail is the 3 at the end. And the uncertain digit in the last nail is this 3 in the 4th decimal place. So if I take those into consideration, and I kind of highlight it here, this number is uncertain, and this number is uncertain. Now remember, we can only ever have one uncertain digit in any measured or calculated value. So right here we have 2, which is the one that we have to keep. Which one do we have to discard? Well, we can't discard the hundredths place, because if we discard the hundredths place, well, all the other numbers would just move up to replace it. They become uncertain as well. Everything to the right of the 100ths place is what we're ultimately going to have to eliminate, because those digits are all uncertain as well, and we need to limit our uncertainty. So the true answer, the answer that we would actually report for this, is 40.36 grams. And actually, let me double check that. I think, oh, we got a rounding issue. My apologies. This would actually be 40.37 grams. So when we have multiple uncertain digits after a calculation, we have to choose the one that is going to eliminate all the other ones and get us back to one uncertain digit. And so that usually means we have to reduce the number of decimal places, reduce the number of significant figures. Also means that we have to evaluate, okay, in that spot, how do I round? And the rule that we use here is 5 and up. If the number next to that uncertain digit is 5 or above, we're going to round it up to the next digit. If the digit is below 5, then we'll just leave it as it was. So the actual calculated value here, the reported value would be 40.37 grams. And this would only have the one uncertain digit. That one uncertain digit is this 7 right there. In the 100ths place, just like we saw with the first 2 nails. And so this brings us into a larger discussion overall of significant figures. And when it comes to significant figures, there are some rules and guidelines that we need to follow. So one of the guidelines that we need to follow regards zeros. The guideline is this: when zeros start or end a number, they do not count as significant figures unless a decimal point is present and a non-zero number has shown first. So what does that really mean? That means that numbers like this where I've got a big, heavy trail of zeros followed by some numbers afterward, none of these zeros count. Only the numbers that came after, the non-zero numbers, actually count. Same thing if I have numbers that are making a number really, really, really big. So I've got 3.5 million here. All of the zeros after that 5 are insignificant. But if I have a number like 4.50, this 0 is significant because it comes after a decimal place and there are non-zero numbers in front of it. So these ones didn't count because they were opening numbers. Even though there was a decimal place, there wasn't a non-zero number until we got to the 5. If I had added a 0 at the end here, that 0 would have been significant because it is now after a non-zero number. One way to make sure that we take care of some of that confusion is through the use of scientific notation. Scientific notation is a great way of kind of clearing that up because in your scientific notation, you will show exactly how many significant figures are supposed to be there. No more, no less. So if you have a number like this, 3.5 million, and you need to show it with 3 significant figures, well, you can't do it this way because this only shows 2. What you would have to do, if you put it into scientific notation, would be 3.50 times 10 to the 6th. Scientific notation shows you exactly how many significant figures are supposed to be there and also shows you the extent of the value of the number. Remember, positive exponents move that decimal place to the right. Negative exponents move that decimal place to the left. So generally speaking, positive exponents are larger numbers. Negative exponents are smaller numbers. So that's the first rule and guidelines for significant figures. Second, multiplying and dividing. When we're multiplying and dividing, what we need to keep track of are the number of significant figures that are in the calculation, not the number of decimal places that are there. Rule of thumb, do not round your answer until after you've done all of the multiplications and divisions. Every time you round a calculation, you are introducing small amounts of error to that calculation, because every one of those times you have to incorporate significant figures, you have to potentially round it up or round it down. If you've got a string of multiplications and divisions to do all of them all at once, and then once you hit enter or execute or equals, then you do your rounding at the end of that step. When adding and subtracting, our rules are pretty much in reverse. We keep track of decimal places, or the decimal place, not the number of significant figures, but we hold the same rule also. If I have a long string of adding and subtracting to do, don't round anything until the very end. So those are our general rules for significant figures. Now you're going to do a post-lecture that is due Sunday night on significant figures. You're going to go through, the lecture packet actually has a series of PowerPoint slides that kind of go through this again, along with an activity that you need to do to kind of work your way through some of those processes and problems. What we're going to move into now, though, is one of the more common applications of significant figures, of adding, subtracting, multiplying, and dividing, and that is unit conversion. So unit conversion involves two things. First of all, we have some kind of equality. We have something that shows that is equal to something else. In the case of the example problem here, there is an equality between kilometers and miles. 1 mile is 0.6214, 1 kilometer is 0.6241 or 14 miles. I'll get it right eventually. With that equality, we can turn anything that we can hook together with equal signs into a fraction. And when we multiply a measured value by either one of these fractions, it is essentially the same as multiplying it by 1, since the two values in the numerator and denominator are equal to each other. So from that standpoint, the whole procedure here is all about factor cancellation. If I have units that I want and units that I'm trying to convert out of, setting up the fraction appropriately so that I have units of the thing I'm trying to convert out of on top of the fraction, and units that I'm trying to convert into, the two units that are the same, one should be in the numerator, one should be in the denominator. And if it's that way, they both cancel out. I'm left with whatever it is that I'm trying to find. So the process itself sounds pretty easy, and for the most part it is. What we have here most often is a matter of coordination, a matter of organization. If you're good at organizing, if you're good at kind of laying out your calculations, unit conversion, factor analysis, pretty easy to do. If you struggle with that kind of thing, if fractions really do bother you from an algebraic standpoint, then this is a little bit more difficult for you. It's something that you're going to have to really work on. This is an example of all of the different types of conversion factors that are in existence between the customary system and the metric or SI system. Now, this is an extensive list. One thing I want to point out to you though, this is not something that you need to memorize. This table is part of the materials that you are allowed to access as part of your end of chapter review kinds of materials. So you will be provided this in some kind of way in the exam, in the test, however you want to put it. So don't sweat over the idea of, oh, I gotta memorize how many pounds are in a kilogram. I gotta memorize how many feet are in a meter. You don't have to do any of those things. Now, you still have to be able to convert within the metric system. We talked about that on Wednesday. But as far as these kinds of conversions are concerned, you do not have to concern yourself with memorizing all of them. Let's take a look at a couple of examples, just to kind of get us started. Speed limit on Interstate 70 between Denver, Colorado and Kansas City, Missouri is 75 miles an hour most of the way. How many hours will it take to travel the 604.9 miles between the cities? For the purposes of this problem, we're going to ignore stops, we're going to ignore speed traps, we're going to ignore changes in speed limit as you go between the two cities. The trick to this problem is in the recognition of what does 75 miles an hour mean? Well, the key word here is per. If you see per in any unit, immediately think in your head, fraction. Miles per hour means miles divided by hours. So if we say something is going 75 miles per hour, that means that our exchange rate is that 75 miles is equal to 1 hour. And so if I have a distance of 604.9 miles that need to be traveled, I need to set up my fraction in such a way that miles gets canceled out and hours get left behind. Now, as far as fractions are concerned, my initial unit has no denominator, so we can think of the denominator in this case as a 1. I have miles in the numerator, which means I should have miles in the denominator of my conversion factor. And therefore hours in the numerator. The rate is 1 hour for every 75 miles. And I can see that in doing so, no unit in the denominator here, so it doesn't cancel with anything. Miles in the numerator here, miles in the denominator there, they cancel out. End result, $604.9 divided by 75. And the calculator spits out this, 8.06533333 hours. Now, given our talk about significant figures, how many significant figures should come out of this calculation? Okay, you're saying 1. Why?
Because the miles, I know, four.
Okay. Okay, we've changed our answer to 4 because there are 4 significant figures in the miles. All right, Jaron, is that you back there? Now, what do you got? 2? Okay, why 2?
Original one was 604.9 miles. You have to round it up to 8.1 miles or 8.1 hours, which would be 260.
Okay, so it's not because of the miles. What do we know about the speed? 75 miles an hour. Is that an exact value, or is that going to be a measured value? If I get in my car and set my cruise control to 75 miles an hour, is it going to be exactly 75 miles an hour? Do I have any way of knowing that, really? It's going to be some kind of a measurement. And as a measurement, it counts towards significant figures, which means I have 2 significant figures in my conversion, 4 in my measurement here. I need to round this to 2. I need to round it to the fewest significant figures available. 8.1 hours is the correct answer as a result. So this is where we can get into a lot of kind of tricky gray areas with significant figures, is making sure that we're applying our rules consistently and correctly in all of our cases. Any questions about this example before we move on to another one? All right, here's a second type of problem that you can run into. This is called a combination unit. We're talking about fuel economy. We're talking about a car that has a fuel economy rating of 41.7 miles per gallon. So that's how it would be sold here. If that same car were being sold in Europe, its fuel efficiency would be rated in kilometers per liter. Let's go ahead and convert that. So in this case, what we have is 41.7 miles over 1 gallon of fuel. What we're going to need to do ultimately here is we're going to have to do a series of conversions to turn the miles into the kilometers and to turn the gallons into liters. Now, some of you may know some of these conversions off the top of your head. I certainly don't. So what I'm going to need to do, not all of that, is let's go back and the conversions that we need to pull are miles to kilometers So that looks like a good one right there. And gallons into liters. Good one right there as well. So these are the ones I'm going to have to pull out. The order in which I do them doesn't matter. What matters is that I get the right numbers in the right places. So 1 mile is 1.609 kilometers. And 1 gallon is 3.785 liters. Right. We'll go back to the other slide to give us a little more room to work. So before we do the calculations, let's make sure that everything is canceling out the way that it should. I see I have miles in the numerator here and in the denominator here. So that's good, that cancels out. Here I've got gallons in the denominator and gallons in the denominator. Hold on a second. Gallons isn't canceling out here. In fact, what I now have is kilometers times liters over gallons squared. That's not what I'm being asked for. So when you have a unit here in the denominator like this, what you want to do is make sure that it's in the numerator of your conversion factor so that it ultimately cancels out. Now we've got what we need. We can do the last step. Last step is to do all the numbers. 41.7 multiplied by 1.609 divided by 3.785. Calculator spits out 17.7266 kilometers per liter. How many significant figures do we need to run here? Answer here is 3. I've got 3 significant figures in my initial measurement. Both of my conversion factors have 4 significant figures. Remember, when we multiply and divide, we go to the smallest number of significant figures, which would be 3. So I'm going to round this to 17.7 kilometers per liter. And that is going to be the answer that we would report for this efficiency rating. Now, there is one other type of problem that we can encounter with regard to dimensional analysis, and that has to do with what if one of my units is square or cubed, and I don't have a conversion immediately on hand for it. So let's just say, for the sake of brief argument here, that we were asked to convert 35 square inches to square feet. Well, most of us off the top of our heads don't know the conversion between square inches and square feet. Again, I don't. But what we do know is that there is a conversion that we can readily find for going between inches and feet. We know that there are 12 inches in every foot. Now to get that to square, well, we would just have to do that operation twice. So if I did the operation twice, inches times inches is squared inches. So there it goes. Feet times feet is square feet. 35 divided by 12, divided by 12. We get an answer here to two significant figures, 0.24 square feet. So those are the three primary types of unit conversion problems that you can encounter. Direct conversion, combination conversions where you have units in the numerator and the denominator to convert, and then exponential conversions. We'll talk more about these on Monday. That should give you a really good head start, not only on the significant figures post-lecture, but if you want to get a jump start on that homework and that stuff that's getting you prepped for the quiz on Tuesday, it'll help a lot there as well. Have a great weekend.